Hello everyone, welcome to a new video on group theory. Let's put some nice music and let's talk about some beautiful mathematics. Today we talk about cyclicity. So let's start with a few preliminaries. What do we mean by this? By this A in between this angle brackets that I believe they're called chevrons. Okay, this is the set of all the integer powers of A. Okay, let's write them down a little formally. There's all the integer power of A. So the powers A to the n such that n is an integer. Okay. Okay, what do we mean by this? This is the set of A to the negative 2, A to the negative 1, A to the power 0, A square, and so on. However, let's start with reminding ourselves that we're not doing ordinary algebra, okay? This is abstract algebra. So what does this really mean? To raise first, I forgot. I apologize for this. All this deal is for an A that is an element of a group. Okay? So what does it mean to raise an element of a group to a certain power? Okay? Remember, it does not necessarily mean that, as you do in regular algebra, that you take a number and you raise it to an integer power. Okay, it can be, but it might not be. So it means that if any operation that we always call a star, A square means A star A, or A operated with itself twice. Okay, so this A to the n means A operated with itself n times, no matter what's the operation. Okay, so only in case that our group is equipped with multiplication, then this means A times A times A times A n times. However, if our group is equipped with addition, then A operated with itself n times means A operated with, so our operation is addition, plus A plus A plus A n times. Okay, but if our element was, for instance, a reflection of a geometrical shape, then A to the n power would mean you do the reflection and then you do the fraction again and then you do the reflection again. So is A composed with A, composed with A, composed with A n times. Okay, I hope this is clear. So don't look at this like something that belongs to the realm of ordinary algebra. Okay? Okay. So why is this special? Again, let me write it again. It is a set of all integer power of A. Before I tell you how this is called, I'm going to tell you a nice property and we're going to prove it. So this, if A is an element of G, it is a subgroup of G. Okay, no matter what element you pick, you get the element and raise it to the to an integer power, and you will always get a subgroup equipped with the operation of G, obviously. Okay, so first let's prove it. And remember that we showed that the one-step subgroup test worked. So we don't have to check all the properties. And just to remind ourselves, what makes a set into a subgroup? Okay, if we have a set made by some element of a group and we keep the set with the same operation of the group, if the set is a group itself, then it is a subgroup. And in order to be a group, we need to satisfy it for properties. Okay, closure, associativity, inverses, and identity. And we saw together that we can check them all by doing in only one step, by using in fact the one-step subgroup test. So let's do it. First, let's make clear what we're claiming. So our claim is, if A is an element of G, then this object is a subgroup of G. Okay, so let's prove it. Let's remind ourselves. Let's redefine it here. So let's A be an element of the group, and let this be in the set of the integer power of A. Okay, A to the n such that n is an integer. Okay. So let's remind for 1 second how the one-step subgroup test works. So in order to prove that S, the set S, is a subgroup of G, then we have S must be a non-empty. Okay, if we have a non-empty set of G, so S is a subset of G. Whenever you have two elements, A and B in S, if AB inverse is in S, then S is a subgroup of G. Remember? So let's use this and try to prove this cool fact. Okay. First, we have to make sure that this guy is not empty, and it's somehow really obvious. If this is the set of all the integer powers of A, they're all in this form, then it must be that A is in the set. Okay, A isn't here, so this guy is not empty. Okay, and we can start with the proof. So we know that it's not empty. Let's pick two elements inside of it. So what are our elements? Our elements are in this form. They're all integer power of A. We need two elements. Okay, so let's do this. Let S and T be be integers. Okay, and observe, and let's pick these two elements, A to the S and A to the T, since are element of A. Okay, now let's do this trick and let's see if it works. Let's do it. Let's operate A to the S with A to the T inverse. If this guy, if this term, if this element is in the set, we are done. We proved that no matter what's the group, no matter what is the element, this guy is always a subgroup of G, which is a very, very beautiful fact. Okay, so what is this? This is A to the S operated with A to the negative T, which is in turn A to the power S minus T. S and T are integers, and we know that integers are closed under subtractions, or more formally under addition. So S plus minus T is an integer. This guy is an integer. In the set, there are only elements in the form A raised to the power of an integer. like we have it here. So this is indeed an element of the set. So we showed, we proved that A is indeed a subgroup of G. Okay, and we are done. Now, if A is a proper subgroup of G, then this guy is called a cyclic subgroup. But there's a chance that by raising A, by operating A with itself, all the integers times, you generate all the group. In this case, we have, and these guys are equal, and it follows that G is a cyclic group. Okay, so we just explained what is a cyclic group. Again, if we have an element of G, okay, and we raise the element to all the integers powers, and by doing so I generate all the elements of G, then G is cyclic. Let's make a few examples. So let's make an example of both. Okay, let me take a group that I like and that I use it all the time. It is very useful. I made a particular study on it, and it turned out being a group with very nice properties. So let's use U14. Okay, so the group of all the positive integers less than 14 and coprime with 14. So it is the group it contains 1, 3, 5, 9, 11, and 13. Okay, equipped with multiplication modulo 14. Now let's analyze this subgroup. Okay, we already know that this is a subgroup equipped with multiplication modulo 14. We proved that no matter what's the element, no matter what's the group, if this is an element of a group, of this group, and is equipped with the same operation, then it is a subgroup of U14. But let's establish if U14 is actually cyclic. So, what is this? This is, remember, 3 to the negative 2, 3 to the negative 1, 3 to the 0, 3 square, 3 cube, and so on. Okay, modulo 14. I wrote them down like this, but it's going to be 3 square modulo 14, 3 to the third power modulo 14, and so on. So let's see what this group actually is. Okay, so let's start with the positive, and then this will give me the chance to explain what it means to raise, to operate an element negative integer times. Okay, because let me show you this. For instance, this guy, 3 to the negative 2, it is not 1 over 3 squared. Okay, in this case it is not. Okay, even if we are equipped with multiplication, but in modular multiplication this does not hold. Okay, and we'll see why. So let's for the moment use the positive integer powers. Okay, so let's notice that 3 to the 0 power mod 14 is 1. 3, let me do it this way. Let me do the easiest, just 1. 3 to the first power is 3, mod 14 is 3. I don't have to write it down. 3 square equal 9, mod 14 is 9. 3 to the third is equal to 27, okay, mod 14 is equal to 13. And then we have we have 3 to the fourth power is equal to 81, mod 14 is equal 11, and then 3 to the fifth power is equal to 243, mod 14 is equal to 5. Now we have to stop and let's analyze this. How many elements does U14 contains? 1, 2, 3, 4, 5, and 6. Okay, so how many times do you think you can raise an element to a power? So to how many powers you can raise an element without repeat, okay, without being redundant. So since the group is closed, okay, under the operation, and there are 1, 2, 3, 4, 5, 6 elements, okay, no matter how you combine the elements, okay, you're only gonna have 6 results, okay. So if you get 6 different results, then for many reasons, I'm gonna show you another one, then you should stop. And in fact we generated 1, we generated 3, 1, 3, we generated 9, we generated 13, 11, and 5. Okay, we generated all the elements of the group by raising an element of the group to all the integer powers. Now, why don't we have to raise 3 to the 6th power? Note that 3 to the 6th power will be 3 times 3 to the 5th power, which we already know that is going to be 3 times 3 to the 5th power, which is 5. Okay, it's going to be 15, which is congruent to 1 mod 14. We already have 1. Okay, so all the other combinations of this will be redundant. So we just saw that we generated all the elements of U14, so we can say that this is equal to U14. Remember, if this condition holds, then U14 is a cyclic group because it has at least one element that it can have more than one, okay, but it has at least one element that, raised by all integer powers, regenerates all the group. Now we're going to see an example where this doesn't happen, but before this, let me talk about what does this mean. Okay, 3 to the negative 1, 3 to the negative 2, for instance. Since we just said that this is not 1 over 3 squared, then what is this? Okay, this is 3 to the negative 1 squared, right? What is 3 to the negative 1? What is confusing is the way I'm reading it, okay? So we shouldn't ever read 3 to the negative 1 in abstract algebra. But this is, remember, what is this element on respect to this? This is the inverse of A. So this is the inverse of 3 mod with multiplication modulo 14, okay? Remember, this is the element of the group which is equipped with multiplication modulo 14. This is the inverse of 3. What is the inverse of 3? Equipped with multiplication modulo 14 is the element, okay, such that 3 times 3 inverse, okay, generates the identity. Remember, A operator with A inverse is equal to the identity. What is the identity of our group? 1. Not 14. Okay? So 3 times 3 inverse is equal 1 mod 14. And we know that 3 times 5. Okay? In fact, 3 times 5 is 15. Okay? 15, which is congruent to 1 mod 14. I hope it's clear. When you see 3 inverse, you have to substitute it with the inverse of 3 in the group. Okay? Find, when you see 3 to the negative 1, think 3 inverse and substitute it with the inverse of 3. Find it in the group and substitute. For instance, if you had 5, okay, we already know, but if you had 5 to the negative 2, then you have to transform it to 5 to the negative 1 square, which is the inverse of 5 square. What's the inverse of 5? Well, we just found it here. It's going to be 3. So this is going to be equal 3 square. Okay? Which is equal to 9. Coming back on this one, 3 to the negative 1, 3 inverse square is going to be 5 square mod 14 equal to 25 mod 14, which is congruent to 11. Okay? Let's move to another subgroup. So let's take let's take another group. Let's take the 8. Okay, what is the 8? Is the set of all the positive integers, 0 included, less than 8, equipped with addition modulo 8. So it's going to be 0, 1, 2, 3, 4, 5, 6, and 7. Okay, equipped with multiplication modulo 8. Let's analyze this term. So this term is, let's write it down here, is the set of all the integers power of 2, which is 2 to the negative 2, 2 inverse, or as we saw before, I wanted to say to the negative 1, or I just said it to inverse, 2 to the power 0, 2, 2 square, 2 cube, and so on. However, let's pay attention, we are equipped with addition. We have addition modulo 8. So what is this? So let's start with only positive integers, and we'll see that it's going to be enough without calling all the inverses. 2 to the first power is just 2. Alright? 2 to the second power is 2 operated with itself twice. 2 operated with itself twice. Okay? Which is 4 mod 8. Okay? 2 to the third power is 2 plus 2 plus 2, which is equal to 6. 2 operated 4 times is 2 plus 2 plus 2 plus 2, which is equal 8 mod 8, which is equal 0. Okay? Now, what do you think is going to happen? What would be 2 to the fifth power? 2 to the fifth power will be obviously if you add another 2, okay? If you add another 2, you add another 2 to 0, and you're gonna go back in this. In fact, 2 to the fifth power will be 2 to the first power, 2, operated with 2 to the fourth power. which is 2 operated with, I should have said operated with, our operation is addition plus 2 to the 4th power, which is 0. And is in fact 2 mod 8, which is 2. So the subgroup of all the integer powers of 2 generated 0, 2, 4, and 6. And that's it. So we can say that this is a proper subgroup of Z8. Okay. However, I was about to say, so Z8 is not a cyclic group. No, you cannot say. In fact, it is, and I challenge you to prove it. But it is not generated by 2. Okay, so the element, like we said before, okay, what is it? 3, if we raise 3 to all the integer powers with multiplication modulo 14, generates U14, the whole group. So 3, it's called a generator of U14. So this is a generator of the group. In this case, 2, it is not a generator of Z8. Okay, it doesn't tell about if the group is cyclic or not, but it's not cyclic because of this. 2 is not a generator. Okay, let's do a quick recap. We saw that this is cyclic. Okay, why is it called cyclic? Do you see that by operating the element, by operating an element with an integer, an integer's amount of times of all the integers, we get into a cycle. Okay, is a pretty obvious in finite groups. If you have a finite groups, you'll see that the number of the elements of the group is finite, but you have an infinite amount of powers, okay, an infinite amount of integers. So by raising an element to all these integers, you're not gonna create more elements than the elements of the group, so they're going to repeat. Okay, and this is why the group is called, the group or the subgroup is called cyclic, because you're going to get into a cycle of generating the same elements over and over, in case that the group is finite. So we saw that this is for A be an element of any group G, this is a subgroup of G. We proved it, and we saw that this can be a proper subgroup, like in this case, or generate the whole group. If A generates the whole group, then the group is called cyclic. And here you know when a group is cyclic. We're going to talk about nice properties of cyclic groups later on. Maybe we'll do some problems. Thank you very much for watching. I hope this was helpful and I didn't confuse you. I'll see you in the next video.